Okay, so in the last video, we built up this idea of these Riemann sums, these rectangles that we're essentially imposing over a function to be able to estimate the area underneath of a function. So let's go ahead and see what that looks like when we're given an example with a table. So suppose a car is moving with increasing velocity that we measure, and we measure the car's velocity every 2 seconds, and it obtains essentially the data in the table that we're given here. So we want to estimate the distance traveled in that 10 seconds. So we kind of want to do what we were doing in the beginning where we want to find the area underneath of this function. Well, let's draw what this function would look like. And we don't need to do that all the time, but I think it's going to be good for this one to really see what's going on here. So we have 2, 4, 6, 8, and 10. And then let's do 10, 20, 30, 40, 50. So let's go ahead and plot those points, very roughly. It doesn't have to be perfect. So we have 0, 20, 2, 30, 4, 38, 6, 44, 8, 48, and then 10, 50. So it kind of starts like sloping off after a while, if you will. Let's go ahead and just plot that point up on the line that I just drew. So essentially, this is what the graph would kind of look like. Maybe it's not perfect, but it gets us the general idea. Now, when we're given a table, we're not told how many rectangles to break this up into, how many pieces we're taking. Sometimes we'll be told, but in this case, we're not. So we kind of get to take as many as we want. Whenever you get to choose, you should usually take as many as you can. So we're essentially going to say, let's break this up at essentially every piece that we can. So let's break it up at 2, at 4, at 6, at 8, and then essentially stop at 10. So we'll stop at 10. And we essentially want to find that area underneath of that, but we can't find it exactly yet because that's not a shape we know the area of. It's not quite a rectangle, it's not quite a trapezoid, it's not quite a quarter of a circle. So we need to use this idea of using rectangles. Now, we're going to find essentially both estimates that we talked about before, the left side and the right side. You don't usually have to find both. Sometimes it's a good idea, but you don't necessarily have to. But in this case, we're going to find both. So let's go ahead and start with the right-hand sum. And that's usually what it's referred to, the right-hand and the left-hand sum. Sometimes it'll be right side or left side sum, but I'll usually refer to them as the right-hand sum and the left-hand sum. So what that means is essentially, notice that all of our rectangles essentially have a width of 2 because the distance between, each of our pieces is 2. So all of our rectangles are going to have width 2, and now we just need to figure out what their heights are going to be. So again, we're kind of breaking it up into these pieces from 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. So if we take our first piece from 0 to 2, well, what's the right side of that? That's at 2. So we're going to go up to the function at 2, and that's going to be the height we're going to use. So essentially the first height we're going to use for our right-hand sum is going to be that 30 that's attached to the 2. And then our next rectangle goes from 2 to 4. Well, what's the right side of that? It's 4. So we're going to go up to the function at 4, and we're going to use that height. Well, what's the height at 4? Well, that's going to be 38. And then we go from 4 to 6. What's the right side of that? It's 6. So we're going to go up to the function at 6 and use that for our rectangle. Well, what's the height at 6? That's 44. Then our next rectangle is from 6 to 8. What's the right side of that? It's 8. So we're going to go up to the function at 8 and use that for our rectangle. What's the height at 8? It's 48. And then our last rectangle is from 8 to 10. The right side of that is at 10. So we're going to use that piece for the rectangle in the last one, and that has a height of 50. So our Riemann sum, which is again just the name for these kind of sums of these areas of these rectangles, is going to be essentially, so we're going to have 2 times something in each case. So that first rectangle, let me kind of give these names. So we have our first rectangle, our second rectangle, our third rectangle, our fourth rectangle, and our fifth rectangle. So our rectangle 1 has a width of 2 and a height of 30. And then our rectangle 2 has a width of 2 and a height of 38. Rectangle 3, width of 2, height of 44. rectangle 4, width of 2, height of 48, and then rectangle 5, width of 2, height of 50. So we have all the areas of all of those rectangles. If we punch that into a calculator, we will get 420, and this will be in feet since it's a distance and we're given feet per second. So our distance here will be in feet. So we can estimate that it goes 420 feet if we use our right-hand sum. So let's go ahead and now use our left-hand sum. So we're going to do the same kind of idea, but we're going to choose different y values. So we have our left-hand sum. And I think I switched around. I did. I switched around the colors. I meant to keep them consistent, but hopefully it makes sense what I'm trying to do here. So the colors are now unfortunately flip-flopped. So let me try to do this to make it clear. The red now turned out to be the right-hand sum, and the blue is going to be the left. So our first rectangle is from 0 to 2. What's the left side of that interval? It's 0, so we're going to use the y value at 0. That's going to give us the height of our rectangle. Second rectangle is between 2 and 4. The left side is 2, so we're going to use that as our height for our rectangle. So on and so forth. So from 2 to 6, left-hand side is 4, so we're going to use 4. Oh, I haven't been writing down the heights. Let's go ahead and write those. So the height at 0 is 20, so that's going to be the height of our first rectangle here. And then the height at 2 is 30. And then the height at 4 is 38. Our fourth rectangle is from 6 to 8, so we'll use the height at 6. Height at 6 is 44. And then our last rectangle from 8 to 10, left-hand side will be at 8. So the height of that last rectangle will be the height at 8, which was 48. So our sum here, again, all of the rectangles have a width of 2. That hasn't changed. Our kind of pieces that we're breaking it up into have a width of 2. So we're going to have 2 times 20 plus 2 times 30 plus 2 times 38, 2 times 44, and 2 times 48. And these are still, matching up with their rectangles kind of in the above example. If you punch that into a calculator, you are going to get 360 miles. Sorry, feet. 360 feet. So, two different estimations. Now also look at this kind of picture we have on the left here. Notice that all of the red rectangles kind of end up above the function. That last one's a little iffy. It gets pretty gosh darn close. But those first four are pretty decently above the function where it should be. And then all of the blue ones end up below. All of the ones from the left-hand sum end up below the actual function. In this specific case, that's not a coincidence. So we have essentially those right-hand sums, the rectangles in the right-hand sum are overestimating, and the rectangles in the left-hand sum are underestimating. So we have in some situations, but not all, we can look to find what we call either an overestimation or an underestimation. So that's going to provide either a too large or a too small estimate respectively. So overestimation too large, underestimation too small. So a function must be purely increasing or purely decreasing on an interval in question for these specifications to hold. And I'll explain why in a second. So let's draw a couple pictures. We're going to have 4 cases, and we're going to leave some space at the bottom to kind of show why it has to be purely increasing or purely decreasing. Now I know there's lots of functions that are increasing and decreasing, but let's just go ahead and draw these little simple cases. So we have 2 that are increasing and 2 that are decreasing. So let's go ahead, I'm going to match the color back to the original thing. So the left-hand side is going to be red, and the right-hand side is going to be blue. So it matches the original thing that we ended with in the last video. So let's say I want to take a left-hand side of this increasing piece here. So if I take a left-hand sum, essentially what I'm going to end up with, if I just break it up into a couple pieces, I'm just doing something kind of generic here. So if I break it up, let's say 4 pieces, and I do a left-hand side here, notice that all of those rectangles end up below the actual function. So this isn't going to end up being an underestimate. Now let's go ahead and jump over a little bit to the right-hand side on this same type of function. So what if we do a right-hand side? Well, if we split it up again, maybe into 4 pieces, and we take the right-hand endpoint to be our height, we're going to get something that looks relatively like this. Notice that all of those rectangles end up above the function. So in this case, this would end up being an overestimate. Now when we look at these in terms of the decreasing function, it kind of changes. So let's start with a left-hand sum for the decreasing piece. So if we again kind of split it into 4 rectangles here, and we use the left side of the intervals in each cases, notice that since the function's decreasing now, all of those rectangles ended up above the function. So in terms of a left-hand sum on a decreasing function, it ends up being an overestimate. And then if we go ahead and do a right-hand sum on a decreasing, we will get something that looks like this. So 4 pieces again. Now this last piece is almost going to kind of fall flat against the function because the last piece is essentially at the x-axis. So in this case, when we do a right-hand sum, all of the rectangles end up below the function, so it's going to end up being an underestimate. So there isn't a relationship between right and left versus over and under. It kind of depends on whether the function is increasing or decreasing. Now, I also said that it has to be purely increasing and purely decreasing. So say we took some function that looks like this, and say I wanted to look at a right-hand side sum. So if I looked at a right-hand side sum and I just break this up into some generic, pieces here, notice that as I'm going along, some of them are ending up above the function and some of them are ending up below the function. And let's go ahead and stop here. So in this case, since the function is kind of increasing in some pieces and decreasing in others, we can't say whether it's an overestimation or an underestimation because we have some pieces that overestimate and some pieces that underestimate. Now, in terms of your Book and Wiley really like to use underestimates and overestimates. I personally will always specify something as a left-hand sum or a right-hand sum because there's this ambiguity between is it a right hand or a left hand when you just say over or underestimate. But when Wiley or your book, if you see it say overestimate or underestimate, you just have to consider, is that function increasing, is that function decreasing, and then kind of come back to this idea to figure out, okay, am I finding a right hand or a left hand sum? But in terms of the questions that I personally write, I will always specify right hand or left hand sum. Now, in general, I can ask questions where I say, here's a graph, here's the, rectangles drawn out for you. Is this an overestimation or an underestimation? I do ask questions like that, but when I want you to actually find the sum, I want you to calculate it, I will personally specify right-hand side or left-hand side. So we're going to stop that video here. We're going to do 2 more examples in the last video.